ሰላም እንዴት ናችሁ? ዛሬ በሶስተኛ ጊዜ በወርክሺት ሶሉሽን ተመልሻለሁ። ይህ ወርክሺት የተዘጋጀው ለቤዚክ ማትማቲክስ ፎር ናቹራል ሳይንስ ወይም ደግሞ ማትስ 1011 ለሶስተኛው ቻፕተር ኦን ፋንክሽን ላይ የተዘጋጀ ናቸው። ስለዚህ እነሱን በጋራ እናያለን ማለት ነው። እዚህ በቀጥታ በወደ ጥያቄዎቹ ከመግባቴ በፊት ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ሰዎች ካላችሁ ቻናሉን ሰብስክራይብ እና ይህን ቪዲዮ ላይክ በማድረግ ብትጀምሩ ደስ ይለኛል። ስለዚህ በቀጥታ ወደ ጥያቄዎቹ እንሄዳለን። The first question is this one, that is question number 1. It says consider set A containing elements 1 and 2 and B containing n-d. Then the first question under this could be list all elements in A cross B. So in order to determine the cross product of these two sets, especially all the elements of the cross product of these two, let us see how we can, or simply how the cross product of two sets is related to that of the number of elements of the two given sets. We know that A cross B is equal to the set containing AB, so that the first coordinate is select from first set A, and second coordinate B is an element of second set B. And therefore, due to this definition, the cross product of these two could be each and every element of the first set, that simply set A, must be paired with every element of second set. Similarly, the second element of the first set must also be paired with each and every element of second set. So that in this case, this one first element of A must be paired with S, so that we have one S which is an element of A cross B. Again, one could be paired with the second element of set B, so that one T could be an element of its cross product, and second element of set A, that is 2 with S and 2 with T, so that this is the Cartesian product of these two sets, A and B. And as you know, or simply as we clearly observe here, the number of elements of this one, that is A cross B, is 4 ordered pairs, and this will have a direct relationship with respect to the number of elements of set A and set B. That is the number of elements of A cross B if A and B are finite set. That means so that the number of elements of A cross B could be a direct product of the number of elements of A and number of elements of set B. The second question under the same consideration could be, well, asked just to list all the relations R from A to B. We know that a relation from R to B is any subset of the cross product of any two sets. You know this. That is, we have this definition first. A relation from A to B is simply any subset of A cross B. Therefore, especially the number of relations, or simply the number of relations that can be constructed from this set A into that of this one, that seems set B is that, since the cardinality of A cross B is equal to number of A times number of B, we have 4. Therefore, the possible subsets of A cross B, which can be considered as a relation from A into that of B, could be to the power of the number of elements of their cross product, which is to the power of 4, which is 16 relations, so that we can have possibly 16 relations that can be constructed from A into B whenever A and B are with two number of elements each. Therefore, we have this one, that simply there are possible subsets. These are possible subsets of A cross B, including this one, that simply implicit, because implicit is also a subset of any set. The third one, that simply see, list all functions functions F from A to B. We know that a function is said to be a function from an unimplicit set A to that of set B, if and only if the domain of the given function, the first set, that's set A, so that they hit the criteria for the given function from A to B to be a function. That means a function that is f, which maps from A to that of B, assigns exactly one element of B to each element of set A. For each element of set A, that means there must not be an element which is left without mapping for the first set that's simply set A. So that based on this criteria or simple definition, for each of 1 and 2, which is an element of A, we choose, or simply we must choose one of these two, either S or T, which is an element of B. So that's the first function could be 1, which is the first element of set A may be paired with S, and the second element that's simply set the 2, which is an element of A, can be paired with the same it's the same element, first element of this one, that is S. They hit the first possibility. It is a function because 1 and 2 may have the same image, but there is no repetition of a domain. The second function could be 1 can be paired with S and 2 can be paired with T. The difference is, in the first case here, 1 and 2 we are having the same image, that is S, but 1 and 2 here have their own unique images. The third one could be 1 can be paired with T and 2 can be paired with S. And lastly, the last one could be 1 can be paired with T and 2 can be paired with T, having the same image like that of S here. Therefore, these are the total number of functions that can be constructed or simply mapped from A, this A, having these two elements to this set that's simply set B. The second question, we are given this information, that is, we are given set A containing elements W, X, Y, and Z, and B containing these three elements. Each of the following sets is a relation from A to that of B. So we are asked just to determine which ones are functions from A to B. We are given four alternatives here. So what we are asking here is we are asked just to determine whether the given relations here are functions, not only functions, but also they are functions which are from A into that of set B. Just we have to apply the definition that already we have seen in the previous question. So let us start from the first one. We are given this. Then the first relation we are given based on this would be this one, having simply with three elements. So in order to justify, currently this one or simply this relation is a function, because each and every element of the domain of the given function is paired with exactly one unique element. W is paired with 3. There is no any other image other than that of 3 for W. X has 4 and Y is mapped with 5. But we need to justify whether this function is a function from this set that's simply set A into set B. For this relation R to be a function from A into that of B, the domain of this relation needs to be exactly the first set that's simply set A. Therefore, when we measure this one, a function from A to B must have exactly one ordered pair for each element A and element of A. It says for each, for all, that means. So that's when we check this, R is given to be this one, and then W appears, that is the first element of A appears here, which we with a mapping or simply an image 3. X also appears, yes, it appears, and then it could be paired with, it is already paired with 4. Y also appears and paired with 5, but 0 doesn't appear. There is no, that Z doesn't appear here. That means Z doesn't have any image within this relation R. Therefore, the domain of this relation cannot be the set that's simply set A. Therefore, the relation that is R is not a function from A into that of B. Second one, on the same information, we are given the relation that is R containing these four elements. And also we are asked just to determine whether this relation is a function from A into that of B. So when we check this, W appears and paired with 3, of course here. Similarly, X appears and paired with 4. And also Y appears and paired with 5. Also Z appears and paired with 5. And you clearly observe here, the last two elements of this relation R is Y5 and Z5. That means Y and Z have the same images, and W, X, Y, Z. That means the domain is the elements of that of set A. Therefore, from this, each element of A appears exactly once. There is no repetition, or there is no any element of this one that's simply set A, which has more than one image, so that there is a function from A to B. The next one, see, the relation R is given to be this, W3, X3, Y3, and Z3. And we're asked just to justify again this whether this relation is a function from A to B or not. And when you check this, the image, whether each and every element of A has an image within B, W appears and paired with 3, X also appears and paired with 3 again, Y also appears and paired with 3, even Z appears and paired with the same element, that's simply 3. That is, this is many to one function or relation. Therefore, because each element of A appears once, even though they map to the same element, that's simply 3, and the domain of the given relation is set A, so that there is a function or a constant function from set A into set B. The next one, let R is equal to the same function here, and the relation that is R is given to be this one, and we're asked just to justify again this one is whether it's a function from A to B or not. When we check this, W appears and paired with 3, of course. X also appears and paired with 5. Y also appears and paired with 4. Z appears twice, paired with 3 and 4. Z is paired with 3, Z is paired with 4. So that one of the elements of the domain of this relation, which is the element of A, is paired with more than one element within the elements of set B, which is 3 and data 4, because 3 is different from data 4. So that this is not the property of a function. Therefore, this relation cannot satisfy condition to be a function, so that it is not a function. Okay, question number 3. It is again determining the following relations are functions or not, and we are asking just to state their domain if and range if they are functions or relations generally. So let us see the first one. The first relation we are given here. We know that for the given relation to be a function, each and every element of the domain of the given function must be paired with exactly one element within its range. That means there must not be any element of the domain of the given relation which has more than one image. So that is mathematical definition of a function. So that when we observe here, we know that 1 is paired with 1. There is no any other element or simple image other than 1 for 1. 2 is also paired with 2. 3 is also paired with 4. And 4 is paired with this one, that is 5. So that there is no any element of the first coordinate which has or simply paired with more than one element within the second one. Therefore, this is a function. So this is a function, and the domain and range could be, we know that the domain of every relational function is the set containing all the first coordinates of each of the elements of the given relation, and set containing the second coordinates will be range. So that's here a domain of the given this function will be the set containing 1, 2, 3, and the data 4. And similarly, the sets or simply the outputs or simply the range could be again 1, 2, 4, and this one that is 5. Question number 3C. We are given this relation and we are asked just to just determine whether this relation is a function or not, and we are also asked just to put a domain and range of the function. We know that when we check this, 1 appears twice. 1 is mapped with -2 and 1 is also mapped with +3 here. So that due to the existence of this element, automatically this relation cannot satisfy the condition or cannot be a function. Even though it is not a function, but it is domain could be the set of the first coordinate, that is 1, -2, -1, and 1 here. And the range could be a set containing -2, 0, 2, and 3. -2, 0, 2, and 3. Therefore, the relation is not a function, and its domain is this one. Okay, so the next one, determine if this relation is also a function. That is the same question. So in order to check whether this relation is a function or not, we know that 3 appears twice with 2, and this one that's simply 3, -3 with 2, -3 with 3, that means. And since input -3 has 2 different outputs, 2 and 3, so the relation cannot satisfy the condition to be a function. And the domain is set of the first coordinate, that's -3, as 3 and 5, and its range will be 2, 3, and -5. Then question number 4. We are given a function f of x equal to this quadratic function and g of x to be this linear function, which is x plus 1. Then what we are asked here is we are asked just to find the operation on this one, that is the sum, product, the quotient of f over g and g over f, and the composition f of g of x and g of f of x. So let us see one by one. The first one, that is the sum and the product of these two, we are given that is f of x and g of x here. So that's the sum of these two, that is f plus g of x equal to f of x plus g of x. So when we substitute the values or simply the terms of f of x and g of x in the place of f of x and g of x here, we have 2x squared minus 3 for f of x and x plus 1 for g of x. And if we add them together, since we are adding for the constant terms, we have 2x squared plus x minus 2, which is the sum of these two functions. And the product could be using the same process, f times g of x equal to f of x times g of x, which is equal to 2x squared minus 3 times x plus 1. So that the product of these two could be 2x cubed plus 2x squared minus 3x minus 3. And next, on the same function f of x and g of x, let us see how we can obtain f over g and g over f. We know that f over g of x is equal to f of x over g of x. So that if we substitute f of x, the terms of f of x and g of x, we have 2x squared minus 3 over x plus 1, but this function that is a quotient function will be defined only when the denominator, that's g of x, is non-zero. So that the domain of this function could be the set of real number, except the set real number which can make this one to be zero. In this case, that is x minus 1. so that this is the quotient. Similarly, the quotient of g over f of x could be g of x over f of x, which is equal to x plus 1 over 2x squared minus 3. And the domain of this one could be a set containing set of real number without the real number making the denominator to be 0, but this could be 0 only when either x is plus or minus the square root of 3 over 2. So that the domain of this quotient function could be the set containing all real number without these two elements of positive number, that is plus or minus the square root of 3 over 2. Next, we are given the same function f of x and g of x. We are asked just to find the composition of f composite of g and g composite of f. First, f composite of g of x could be, by definition, it is f of g of x, so that it is f of, but g of x here is this one, that is x plus 1. So we have f of x plus 1. But when we give a function or simply a certain input for f, the output will be twice of the square of the input minus 3. Therefore, this could be the output for x plus 1 within under f could be twice of x plus 1 the whole square minus 3. Then when we further simplify this one, we have twice of the square of this one, that is x squared plus 2x plus 1. We have minus 3. If I distribute this one over here, 2x squared plus 4x plus 2 minus 3, which is equal to 2x squared plus 4x to minus 3, that is minus 1. So that there is the composition of f and g, which is f composite of g whenever f of x is 2x squared minus 3 and g of x is equal to x plus 1. Similarly, g composite of f of x could be g of twice of x squared minus 3, because f of x is 2x squared minus 3, which is equal to the output for g could be the input plus 1. So that it is just 2x squared minus 3 plus 1, which is equal to 2x squared minus 2. That is minus 3 plus 1 is minus 2. So that it is how we can obtain the composition of two functions. Okay, the same question, that question number 5. Again, it is composition, but the function or the relations are given in the set of ordered pairs. The first one, the first relation which we are given here is a set containing 1, 1, 2, 2, and s is 1. We have 3, so let us try to see one by one. The first one is we are asked just to find s composite of r and r composite of s whenever r is this one and s is here. So the first one, that is for s composite of r, by definition we know that S composite of R is the set containing an ordered pair of this one, that is AC. But for this AC to be the element of S composite of R, there must exist B such that AB is an element of R, the first relation, and BC must be an element of, or simply it should be included in S. If this happens, if AB is in R and BC is in S, so that automatically AC must be an element of the composition of S composite of R. Then based on this fact, when we compare and contrast the given elements of S and R here, we have S composite of R. One is an element of R, but one is not within the domain of S here, so that one cannot have any image within S composite of R. Similarly, 2 is an element of the first set here, and 2 is also an element of the domain of S here, so that 2 is mapped with 2 under R, and 2 is mapped with 3 under S, so that 2 must be mapped with 3 under S composite of R. So that's simply 2, 3 could be an element of S or R. And 2 again, 2 again here, 2 is an element of R, that is an element of S, and this implies 2R must be an element of S composite of R. That means 2 could be mapped with 2 itself under R, and these two, which is the image of S, the image of 2A under R, could be a domain for S and map to base 4, so that 2, 4 will be an element of S composite of R. Therefore, the composition that is S composite of R could be an element containing the set containing 2, 3, and 2, 4. The next one, the same type of question, but there might be different elements. We have 2, 3 is an element of S, but 3 is not within the domain of S here, so that 2 cannot have an image on R composite of S. Similarly, 2, 4 is an element of S here, and 4 is not an element of the domain of R here. There is no 4 which is within the domain of this one, so that 2 cannot have any image under R composite of S. Therefore, the composition that is R composite of S is empty set. The next one, that's B for SOR and ROS. Again, whenever R is given to be the set, that's simply this set, and S is this one. So let us see the first one. The composition that is S composite of R, S is here, and R is this one, so that we know that the first case, that's simply for R. We should start from R here. R, that is 1, 2 is an element of R here. 2, 3 is also an element of S here, so that the image of 1 under the composition of S or R could be this one, that is 1, 3. So that 1, 3 must be an element of S or R. Similarly, 1, 2 is an element of R. We have 1, 2 here, and the same element, so that 2, 4 is also an element of S, because 2 is mapped with 2 and that of 3 under S, so that 1, 4 must also be an element of S composite of R. Next, 1, 3, the second element of R here, is an element of R, and 3, 5 is also an element of S, so that 1, 5, the image of the domain of R, that is 1, and the image of 3 under S, which is 5, which is 1, 5 is an element of S composite of R. 4 is an element of R again here. We have 4 within S, within R, and but there is no 4 within S, or 4 is not within the domain of S here, so that this one, that is 2, cannot have an image over here. Lastly, 5, 7 is an element of the relation that is R here, and we have also here 7, 1 is an element of S, so that 5, 1 must be an element of S composite of R. Therefore, the elements of S composite of R could be 1, 3, 1, 4, 1, 5, and 5, 1. The next one, that is question number 5. See again, S composite of R and R composite of F when R and that of S are given in formula. Then the first one, that is for S composite of R, we are given R to be YR, that is the image of under R could be 1 over X minus 1, and S, say that the image of Y under S could be X over X minus 1. Then the composition of these two, that is S composite of R, could be Y is equal to S of R of X, which is equal to S of 1 over X minus 1, because R of X is 1 over X minus 1. So that this could be further simplified to 1 over, because here it is 1 over X minus 1 is our X over X minus 2 with a property of this one, that's simply S, so that when we give 1 over X minus 1 for S, the output could be 1 over X minus 1, that is the input, over the input minus 2. The input over the input minus 2. So that when we further simplify this expression, we have 1 over 1 minus twice of X minus 1. That is, if we subtract 2 from 1 over X minus 1, we have this one, and which is equivalent to 1 over 3 minus 2X. Therefore, the domain of this one, that is with the domain x different from that of 1 for r, and 1 over x minus 1, which is different from that of 2, which implies x is different from that of 3 over 2 for the composition function, which is s composite of r. Similarly, the other, that is for r composite of r, r is given to be this, and s is this one, so that r composite of s could be y is equal to r of s of x, which is r of s of x is x over x minus 1, so that it is r of x over x minus 2. Sorry. Then the heat equivalent with 1 over x over x minus 2 minus 1, which is equal to 1 over x minus 2 over x minus 2, which can be further simplified to x minus 2 over 2. That means taking or simply multiplying the reciprocal. Already x minus x is 0, minus of minus 2 is positive 2, and this could be taken into the denominator term, so that it could be x minus 2 over 2. Therefore, the domain could be x different from 2 for s, because s is here, that is x over x plus x minus 2, so that it becomes undefined at x equal to, so that that is why we should exclude 2 from being an element of the domain of this function. And for x over x and different from that of 1, always true for x different from that of 2. Then the s composite of r could be y is equal to 1 over s minus 2x for x different from that of 1 and 3 over 20. R composite of s could be y is equal to x minus 2 over 2 whenever x different from that of will be the summary. The next one, that's question number 6. Again, on compulsion function, but we are given these 3 questions, and let us see them one by one. The first one, that is a, is given to be, we are asked just to find g of x if f composite of g of x is x squared plus 3x, and one of these two, that is f of x, given to be x plus 5. We are given the compulsion function x squared plus 3x, and one of the function, that is this one, that is the outer function f of x, given to be x plus 5. So we are asked just to find g of x. So we have, using the definition of compulsion function, f composite of g of x is equal to f of g of x, which is equal to x squared plus 2x, which we are given here. But the output for f could be the input plus 5, so that it could be just g of x plus 5. Since f of x is equal to x plus 5, then f of g of x is equal to g of x plus 5. But this is equivalent with x squared plus 3x. So that from this, g of x could be, if I take this one, that's 5 to the right of the equality, we have g of x equal to x squared plus 3x minus 5. Therefore, we can check this one, that is f of g of x is equal to, I must give us this one, that's x squared plus 3x. Therefore, f of g of x would be x squared plus 3x minus 5 plus 5. Then minus 5 plus 5 is already 0, so that becomes x squared plus 3x. Therefore, perfectly, g of x could be x squared plus 3x minus 5 whenever f composite of g of x is equal to x squared plus 3x, and f of x equal to x plus 5. Next, the second one, question number B. We are given f of x equal to e the power of the square root of x, and we are asked just to find g of x, so that f composite of g of x equal to g composite of f of x equal to x. We know that whenever g composite of f of x equal to x, so that the relationship that exists in between g and that of f is that one is the inverse of the other. One could be the inverse of the other. That means g is the inverse of f, or f must be the inverse of g whenever this condition is satisfied. we need g such that f of g of x equal to x and g of f of x equal to x. This means g is equal to f inverse, the inverse function. So that let's find f inverse. In order to find f inverse, let us start by letting y is equal to e the power of the square root of x. So the inverse of this one could be taking the natural logarithm of both sides of this equation. We have ln y is equal to ln of e the power of the square root of x, which is the square root of x. Then squaring both sides, we have the square of ln y is equal to the square root of the radical x, which is x. So that when we try to solve for x is equal to ln y square. Then in interchanging x and that of y, we have f inverse of x, or simply g of x equal to ln x the whole square for x greater than 0. For x greater than 0, so that this is what g of x is. If we unit just to check whether this one is exactly or perfectly the expression for g of x or not, f of g of x needs to be f composite of g of x we are given here, that is x. So f of g of x equal to e the power of the square root of ln x square. The square can be cancelled and become the absolute value of x. The absolute value of x could be, because x is greater than 0 here, e the power of ln x could be x for every x greater than 0. So it is perfectly the function what we need. The next one, that is question number C, that is 6C. Find g composite of h of x whenever g of x is this squared function, the square root of x minus 1, and h of x is x squared plus 1. We know that by definition, g composite of h of x equal to g of h of x, which is equal to g of x squared plus 1, because h of x is x squared plus 1. But the property of this one, that is g, could be whenever we give x for g, the output is always the square root of the input minus 1. So that g of x squared minus 1 could be the square root of x squared plus 1 minus 1. Further, the simplified form of this one could be the square root of x squared, and the square root of x squared is already the absolute value of x. Therefore, the domain could be h of x is x squared plus 1, which is greater than or equal to 1 for all x. So g of h of x will be defined for all x. It could be defined for all x. That's what the absolute value of x, that means. Question number 7 is about these 5 questions, which we are asked just to find, or simply just to justify whether the given relations from functions from R to R are 1 to 1 or on to. So let us see them one by one. First one is determine if f of x equal to 6x minus 1 is 1 to 1 and or on to. We know that a function f is said to be 1 to 1 if and only if f of a is equal to f of b implies a is equal to b. That means a function is said to be 1 to 1 whenever no two elements of the domain of the given function have the same image within the corresponding range. Therefore, in order to check whether this function, that is f of x equal to 6x minus 1 is equal, the 6x minus 1 is 1 to 1 or not, let's assume that f of a is equal to f of b. If we can able to obtain that a is equal to b, so that the function is 1 to 1. But we know that f of a is equal to 6a minus 1, which is equal to f of b, which is 6b minus 1. So that we have 6b is equal to 6b. If we divide both sides by 6, we have a is equal to b. Therefore, for any arbitrary end b, if f of a is equal to f of b, automatically is equal to b, so that the function is 1 to 1. Similarly, for oneness, for every function that is for every y, which is an element of R, that is the domain, that means if there exists at least 1x, which is an element of R, with f of x equal to y, so that the function is said to be an odd function. So that based on this, in order to check the ontoness of this function, let's try to solve for y first. We know that y is equal to 6x minus 1. Then if we try to solve for x, we have x equal to y plus 1. So that for each and every element of this one, that is y, which is an element of R, we can obtain at least 1x, which is the pre-image of this one, that is y, so for which is for y. Therefore, the function is unknown. Therefore, the function that is f of x equal to sx minus 1 is both 1-to-1 and onto. That's bijective or 1-to-1 correspondence. Second function is f of x equal to x squared plus 1. And we're asking just to justify whether this function is 1-to-1 and or onto function. Let us see the 1-to-1ness first. We know that f of 1 is equal to 8. F of minus 1 is also 8. So that two elements of the domain of this function, that is 1 and minus 1, are paired with the same image, that's simply 8. So that this function cannot be an onto function, because since 1 is different from that of 1. So it is not 1-to-1. In order to check its ontoness, we have f of 0 is equal to 7 is the minimum value of this parabola, which opens in the upward direction. So that f of x is greater than or equal to 7 for all x. Thus, for y less than 7, example, if we take y is equal to 0, because the function is from R to R, there is no nx which exists as f of x equal to this one, that's simply 0, so that the function is not onto. Therefore, the function f of x equal to x squared plus 1 is neither 1-to-1 nor onto. The next one, that's simply see, we have the function f of x equal to x cubed. Now that this function is an increasing function. So that whenever a function is a strictly increasing function, it is expected to be 1-to-1 function. Anyways, let us see, it is 1-to-1ness by following the definition. Let f of a is equal to f of b. This implies a cubed is equal to b cubed. Then taking the cube root of both sides of this equation, we have a is equal to b. Therefore, for f of a is equal to f of b, we can have a is equal to b. Therefore, the function is 1-to-1. Yeah, we know that cubic polynomial is strictly increasing, so that every strictly increasing functions are onto function, I mean 1-to-1 functions. In order to check it as 1-to-1, I mean ontoness, let us try to solve for x first. For any y element of R, we have x equal to the cube root of y, so that for any y, we can obtain the corresponding value of x, which could be considered as a pre-image for this y. Therefore, the function is an onto function, because for each and every element of the range of the given function, there exists at least one pre-image within its domain, so that it is 1-to-1. Therefore, the function f of x equal to x cubed is both 1-to-1 and onto, so that it is bijective or 1-to-1 correspondence. The next one, determine f of x equal to 2x plus 1 over x minus 7 is 1-to-1 and or onto. Let us see 1-to-1ness first. We know that the domain is set containing a set of real number without 7, because it's undefined at 7 here. The codomain is R, since it is from R to R, just we are informed at the beginning. Then, in order to check 1-to-1ness, suppose f of a is equal to f of b, so that f of a would be twice of a plus 1 over a minus b, and f of b is to be plus 1 over b minus 7. So when we further simplify this one, if you multiply this one, that's crisscross, we have to be a plus 1 times b minus 7, this is equal to this. Then further simplifying this one, we have twice of AB minus 4B plus B minus 7 is equal to twice of AB minus 14B plus A minus 7. Here we have this one, that is this thing can be cancelled by this one, that is twice of AB, twice of AB. We have 7 again here. This 7 can be cancelled by this one. Again, we have minus 14b minus 14a plus b minus 14b plus a. So when we have this one, that means cancellation. We are given this one minus 14a plus b is equal to minus 14b plus a. And rearranging these terms, we have b plus 14b is equal to a plus 14a. That means taking this one to the right side and bringing this one to the left gives this one, and this implies 15b is equal to 15a. Dividing both sides by 15, we have a is equal to b, so that the function is one-to-one function. For unknown-to-ness, a horizontal asymptote y is equal to 2. That means the horizontal asymptote, this is a rational function with the same degree for the numerator and the denominator, so that when the numerator and denominator of the given function are equal, so that the quotient of the coefficients, the leading coefficients of the two functions could be taken as the horizontal asymptote for the graph of the given function. That is why y is equal to 2, which is y is equal to 2 over 1, because the coefficient of the numerator is 2 and the coefficient of the denominator is 1, so that 2 over 1 or 2 could be the horizontal asymptote. So this divide coefficient is this, so f of x never equals to 2. It never to be exactly is equal to 2, because y is equal to 2 is a horizontal asymptote. The graph may approaches, but it never touches or simply intersects, so that there exists within the range of this function, there is 2, which is an element of the range of the given function, without any measure, so that the function is not an unknown function. Okay, the next one could be question number 8, which is finding the inverse of the given function. So let us start from the first one. The first one could be find the inverse of h of x equal to the cube root of x minus 3. So in order to follow or simply just to have the inverse of the given function, we have usual steps or simple around 3 or 4 steps. The first step will be letting f of x, or simply the image of the arbitrary element of the x within the domain of this function, to be y, so that h of x equal to this function could be taken to be y is equal to the cube root of x minus 3. Then if we try to solve for this x, we have this one, that is y plus 3, that is taking this one to the left side, is equal to the cube root of x. Then taking the cube of both sides, we have y plus 3, the power of 3 is equal to x. Then replacing the variables y and that of x and taking f inverse of x for x, we have y is equal to x plus 3, the power of 3, could be the inverse of the given function, or generally h inverse of x equal to x plus 3, the power of 3. In order to check if we need checking for this one, we know that h inverse of the composition of h inverse of x must be x. So h inverse of x is equal to the cube root of x plus 3, the power of 3 minus 3, which is equal to x plus 3 minus 3, which is what? X. So that exactly h inverse of x is equal to x plus 3, the power of 3 could be the inverse of this one, that is h of x equal to cube root of x minus 3. Similarly, for B, we're asked just to find the inverse of g of x equal to the fifth root of minus x plus 2 over 2. So following the same procedure or simple step, we have g inverse of x is equal to replace, for example, g of x by y first, and it becomes y is equal to the fifth root of minus x plus 2 over 2. And then taking the raising to the fifth power by the power of 5 is equal to minus x plus 2 over 2. And multiply both sides by 2 again, just to make this one, the denominator of this one, to be 1. We have 2 times y the power of 5 is equal to minus x plus 2. Then taking x to the left and this one to the right side, we have x is equal to 2 minus 2 times y the power of 5. Then taking f inverse of x and interchanging x and that of y, we have g inverse of x is equal to 2 minus 2 times x to the power of 5. If you need just to check, g inverse of x must be x, which is equal to the cube root of 2 minus 2x the power of 5 plus 2 over 2, which is equal to the fifth root of, just after distributing this one, if we further simplify this, the fifth root of minus 2 plus 2, this over 2, and which could be, that is 2 plus minus 2 is already 0, which we are left only, and these two can be cancelled by this one, the fifth root of x the power of 5, which is equal to x. So exactly, g inverse of x is equal to 2 minus 2x the power of 5 could be the inverse of g of x, which is given here. Question number 9. Find the range of these functions. So let us see them one by one. Find the range of g of x equal to 2x plus 1. So the range could be g of x is equal to 2x plus 1 is given. It is a linear function with slope 2, which is an increasing function. Then the domain is the set of real numbers. And so that for the range as x approaches to that of negative infinity, when x approaches negative infinity, it's image that g of x will also goes to negative infinity, and when x goes to that of a very large positive number or simply goes to infinity, g of x will also tends to infinity, because this function is an increasing function with a positive slope. And it is continuous, takes on every value since it's polynomial. Hence, the range of this function, that's g of x, is the set of real number. The next one is this rational function. The range of the rational function, x plus 1 over 2x minus 1. So we are given the function f of x equal to x plus 1 over 2x minus 1. So and then solving for x in terms of y, we have y is equal to x plus 1 over 2x minus 1. We have a cross multiplication, that is y times this one, which is y into 2x minus 1 is equal to x plus 1. And taking this one to the left side, we have 2xy minus y. That's distributing this thing diagonally, we x plus 1. Then rearranging these terms, 2x minus x is equal to y plus plus 1. We have x into 2y minus 1, which is equal to y plus 1. Then if we try to solve for x is equal to y plus 1 over 2y minus 1. Then, but this one is undefined whenever y is equal to this one, that is 1 over 2. And is at y is equal to 1 over 2, this expression or rational function is undefined. Therefore, checking for y is equal to 1 over 2 would give 2 is equal to minus 1, which is impossible. Therefore, the range of the given function, that is f, could be r without this fraction, that is 1 over 2, where this is undefined. The third one, the range of h of x equal to the square root of x plus 4 minus 3. So h of x equal to square root of x plus 4 minus 3 is given. Therefore, the domain is that is already correct that the radicand that is x plus 4 needs to be non-negative, so that this must be greater than or equal to 4, and this could be satisfied whenever x is greater than or equal to minus 4. Then this is for all x in the domain, and the minimum value of this one could be that is the square root would be minimum whenever it is 0, so that it could be 0 whenever x is equal to minus 4. But h of minus 4 is equal to 0 minus 3, which is minus 3. Therefore, the minimum value of this functional value of this function h of x is minus 3. At maximum, whenever x approaches infinity, that means when x gets very large positive number, its functional value, that is h of x, will tend to positive infinity. So h of x and also therefore but h of x or simply x can never goes to that of negative infinity because the domain is already greater than or equal to minus 4. So that the range could be from the minimum value of this functional value, which is attained at x equal to minus 4, to positive infinity. Therefore, this is the range. Question number 10. Find the quotient and remainder of the functions given here. So let us see them one by one. Polynomial division, long division method could be applied here. When we divide x squared over x squared, that is the leading term of the numerator, by the leading term of the denominator, we have x. And if we multiply the quotient by the denominator, we have x into x plus 4, which is x squared plus 4x. And if we subtract this product from the numerator here, we have x squared minus 5x plus 8 minus this one, which is minus 9x plus 8. So they hit the first remainder, which is obtained at the first step. Then next, we have to divide this one again by the denominator, the leading coefficient of the term of this one, that is minus 9x over x is minus 9. So this is the first quotient. And if we multiply this one, the quotient, by the denominator, by this one that's minus 9, we have this minus 9x minus 36. And let's subtract this one from minus 9x plus 8 minus of minus 9x minus 36, which is 44. Therefore, this is really the remainder, and the quotient could be x minus 9. Therefore, if we check this, that is by using that of polynomial division algorithm, they hit the quotient, this is the denominator, and this one is the remainder. Then when we multiply these two, we have x squared minus 5x minus 36. If we add the remainder, we have x squared minus 5x plus 8, which is the given function. Similarly, the second one, to execute minus 7x squared plus x plus 4 divided by x minus 4, that is, let's find the remainder and the quotient, which is obtained by dividing this cubic polynomial function by x minus 4. Let's divide the usual, that is long division method, to execute by x. We have 2x squared. And let's multiply the denominator by 2x squared and subtract from the denominator, so that we have this one, the product. And let's subtract to execute minus 7x squared minus to execute minus x squared, which is x squared, and bring down x, so that x squared plus x, and divide the first one, that's simply this difference, by again this one, the leading term of the denominator, which is x. We have x here. Then multiply the denominator by x. We have x squared minus 4x. So that if we subtract this product, the product that is x squared minus 4x from x squared plus x, we have 5x. Then bringing down 4 and 5x plus 4 could be again divisible because we have a linear denominator so that it becomes 5. And then if we multiply the denominator by the quotient which is obtained at this step, we have 5x minus 20, and let's subtract this product from 5x plus 4 which is obtained here. Then the difference could be 24, so that is exactly the remainder which is constant. Therefore the quotient could be 2x squared which is obtained in the first step, x which is obtained in the second step, and 5 which is obtained at this step. And the remainder could be 24. Therefore, this is the last answer for this question. Similarly, the next one, that is question number 10c, 1 minus x squared over x minus 1. We have rewrite the numerator first, 1 minus x squared, as the negative of x squared minus this one, which is a simplification. We have this thing, and then cancelling this one, that is x minus 1, we have minus of x plus 1, which is minus x minus 1, distributing this 1 minus 1 over x plus 1. And therefore, the quotient here is minus x minus 1, and the remainder is already 0. So that's the answer which is obtained by simplification. Question number 11. If p of 4 is equal to 0 and p of x is given to be this cubic polynomial function, we're asked just to find the remaining zeros. We know that this is at degree 3, so that the polynomial function will have 4 either distinct or roots with some multiplicities. But what we are given here is one of the possible roots of this polynomial function is that is 4, because p of 4 is equal to 4, so that 4 is the 0 of this polynomial function. And using the factor theorem, if p of 4 is equal to 0, x minus 4 is one of the possible linear factors of this polynomial function. Therefore, they hit the factor, and then the quotient obtained when p of x is divided by x minus 4 could be, that is already the remainder is 0. We have 2x squared minus 3x minus 2. You can check it. That means this quadratic equation could be obtained by dividing this cubic polynomial function by its factor, that is x minus 4. So that p of x can be expressed as x minus 4 times 2x squared minus 3x minus 2. And again, when we try to factorize this one, that's simply the quadratic expression, and that is the quotient which is obtained there, and that means 2x cubed and 2x squared minus 3x plus 2 could be factorized as 2x plus 1 times x minus 2. So that fully the polynomial function p of x will be factorized as x minus 4, 2x plus 1, and x minus 2. Therefore, the zeros of the polynomial function could be the zeros of each linear factor, so that the zeros could be x equal to 4, which is obtained from x equal to 4, x minus 4 is equal to 0. When we take 2x plus 1 is equal to 0, we can obtain x equal to negative 1 over 2. When we take or assume x minus 2 is equal to 0, x must be 2, so that 4, 2, and negative 1 over 2 are said to be the zeros of the given polynomial function. Therefore, 2 and negative 1 over 2 are the other zeros of the polynomial function other than 4. And next, we are also asked just to find the remaining zeros given that 2 minus 3i is the root of this cubic polynomial function again. We know that one of the possible roots of this polynomial function is given to be the complex number 2 minus 3i, so that by using that of complex conjugate theorem, if this complex number is the root of this polynomial function, its complex conjugate, which is 2 plus 3i, must also be the root of the same polynomial function. So we are left only one root, that is two of the roots of the given polynomial function are complex, which are one is the complex conjugate of the other. Is that their real coefficients or coefficient roots come in conjugate pairs, so that if 2 minus 3i is the root, then its complex conjugate 2 plus 3i must also be the root of the polynomial function. So let the third root be r. Then, by using that of sum of roots formula, for x cubed plus bx squared plus 3x plus d, the sum of roots is equal to minus b over a, which is minus b over a, which is the term of this one, the coefficient of x squared and the coefficient of x cubed. That means, so that in this case, we have a is equal to 2, b is equal to minus 5, so that the sum of these two plus r is equal to minus of minus 5 over 2, which is 5 over 2. And the sum of these two could be 2 minus 3i plus 2 plus 3i could be minus 3i plus 3i could be 0, 2 plus 2 could be 4, so that we are left only 4 plus r is equal to 5 over 2. So that the difference could be taking 4 to the right side, 5 over 2 minus 4, which is equal to 5 over 2 times minus 8 over 2, which is equal to negative 3 over 2. Therefore, 2 minus 3i, 2 plus 3i, and negative 3 over 2 are said to be the zeros of the given polynomial function, so that the others or the remaining zeros of the given polynomial function other than 2 minus 3i could be 2 plus 3i, which is the complex conjugate of this complex number, and negative 3 over 2. Generally, for any polynomial function, for a polynomial function, p of x is equal to n times x to the power of n plus this one, that is general formula. Then we have if r1, r2 up to rn are its roots, and then the sum of the roots of this polynomial function could be the negative of an. It is not an, rather, sorry, it is not an, rather it must be an minus 1. This is not here. N minus 1. N minus 1 over n. Okay, this is the generalization. The next one would be, that is simply question number 11c. We have, or simply we are given a polynomial with roots 1, 2, 3 with multiplicities 3 to 1. We are asked just to find a polynomial in terms of a polynomial with whose roots are 1, 2, and 3 with their corresponding multiplicities. So just to do this, we have multiplicity. Just let us say something about multiplicity with roots with multiplicity. M is said to be multiplicity, or simply R is said to be the root of the given polynomial function with multiplicity m whenever x minus r the power of m is the factor of the given polynomial function. That means whenever x minus r the power of m is the factor of the given polynomial function, this real number that is r is said to be, or a complex number even, is said to be the root of the given polynomial function with multiplicity this times, that is m times. Therefore, when we apply this idea for obtaining the polynomial, the expected polynomial with these roots with their corresponding multiplicities, we have 1 is the root of the given polynomial function with multiplicity 3 times. If we assume that this one is respectively, so that x minus 1 the power of 3 must be the factor of the polynomial function. Similarly, 2 is also the root with multiplicity 2, so that x minus 2 the power of 2 must be the factor of the other possible factor of the polynomial function. And lastly, 3 is the root of the given polynomial function with multiplicity 1, so that x minus 3 is the factor of the polynomial function. Therefore, when we multiply all the factors here, we'll have f of x is equal to, if f of x is the given polynomial, x minus 1 to the power of 3 times x minus the power of 2 times x minus 3, which is equal to this polynomial function. And one thing that you should never forget or simply should remember here is that the degree of the given polynomial function here is 6. And this 6 is simply directly the sum of the multiplicities of the roots of the given polynomial function. That is, all the multiplicities of all the roots of the given polynomial function, which is 2 plus 2 plus 1. That is exactly 6. Next question, number 12. And that is question number 12 will be find rational roots and just sketching the graph of the given function. Let us see the first one. The first polynomial function is f of x is equal to x cubed minus 4x squared minus 7x plus 2 is given. So that the rational roots of the given polynomial function is that when we apply rational root test here, if a certain rational number p over q is the root of the given polynomial function, the denominator, that is p, must be the factor of the constant term, which is 10, and q must be the possible factor of the leading coefficient, in this case that is 1. So that the possible roots of this one are, we know that the factors of the constant term, that is the expected denominator for the rational number, could be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10 itself. Similarly, the possible roots of, factors of the constant term, that is 1, will be only plus or minus 1. Therefore, when we combine this one with respect to, that is, the factors of 10 with the factors of this one, that's simply 1. Whenever the factors of 1 are possibly denominators and factors of 10 are denominators, we have only this one. Therefore, all the rational roots of this polynomial function cannot be out of these numbers. So in order to distinguish which rational numbers are roots of this one, we have to check each of these numbers by substituting in the place of x here, and we have to check whether they can make the polynomial function, that is f of x, to be there or not. For example, if we test for x equal to 1, f of 1 is equal to, if we substitute 1 here, we have 1 minus 4 minus 7 plus 10, which is equal to 0. So that one of the possible rational root of this polynomial function is 1. Then in order to check or simply find the other, if you take, for example, f of 2 is equal to the power of 3, which is 8. 2 squared, that is 4 times 4 is minus 16. 2 times this one is minus 14, which is different from that of 0, so that 2 cannot be the 0 of this polynomial function. Let us check for minus 2, that is f of minus 2 is equal to minus to the power of 3, which is minus 8, minus 2 squared times minus 4, that is negative 16. Negative 2 times this one is positive 14, plus this one could be, this is minus 24, plus 24, that is 0. So that the second rational root of this polynomial, cubic polynomial function, is negative 2. Similarly for 5, f of 5 is also 0. Therefore, all the rational roots of these polynomial functions are rational. And these are, that is 1, negative 2, and 5. Hence, f of x has 3 distinct rational roots, and the roots are minus 2, 1, and 5. Or even using factorization, factor theorem, and combination of remainder theorem, we can easily obtain the root of the given polynomial function. Then for the quadratic expression, that is, if we factorization, that means because already one of the possible rational root of the given polynomial function is this one, that's simply x minus x, 1, so that x minus 1 is factor. So when f of x is divided by x minus 1, the quotient is x squared minus 3x minus 10. Again, if we factorize x squared minus 3x plus 2, it becomes x minus 5 plus times x plus 5. So that fully the factorized form of f of x could be x minus 1 times x minus 5 times x plus 2, so that the roots are 1, 5, and negative 2, as it is obtained previously. Then just to check, sketch the rough graph of the given polynomial function, we need to know, or simply just to have, the degree 3 with positive leading coefficient, so that it could be an increasing. The roots are minus 2, 1, 5, which are the expected x-intercept of the graph of the given function. That means the y-intercept whenever x is 0, that is f of 0 is equal to, that is 10. And also the x-axis at each root, that's simply minus 2, 0, 1, 0, and 5, 0 are the x-intercepts. So the rough graph of the given polynomial function looks like this one. The x-intercept is minus 2, 0, minus 2 is 0, 1, 0, 1 is one of the second root of the given polynomial function, and 3, 0. And it has two turning points, because the curve of a polynomial function, if the degree is n, at most the graph will have n minus 1 number of turning points. And when we assume or simply take x is a very large positive number, so that its functional value will also goes to positive infinity. When x is a very small negative number with a very large absolute value, so that its functional value will decrease indefinitely without any bound. Therefore, roughly the graph of the given function looks like this. Okay, the next one, that is question number B. F of x is again cubic polynomial function with these terms. Therefore, the possible roots for this one is again, the constant term is here 1, that is, but the possible factors of this one, that is 1 is plus or minus 1. And the leading coefficient is 6, so that the possible factors are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So when we combine or simply obtain a fraction or simple rational number by taking plus or minus to be the expected denominator for the expected rational number, and the factors of this one to be the denominator, we have this one. Therefore, if all the roots of these polynomial functions are rationals, so that the roots can never be out of these rational numbers. Therefore, in order to distinguish which rational number is the root of the given polynomial function, let us test for x equals 2. We know that f of 2 is, if we substitute 2 here, we have 3 over 4 plus 1 over 4 minus 2 plus 1, which is already 0. Therefore, this one, that is 1 over 2, is one of the possible rational root of this polynomial function. If 1 over 2 is a rational root, hence using the factor theorem, we know that x minus 1 over 2 must be its factor, so that when we divide this trinomial, or simply the cubic polynomial function by 2x minus 1, which is one of the possible factor of this polynomial function, we have the quotient 2x squared plus 2x minus 2. And the quotient, that's simply this quotient 3x squared plus 2x minus 1 can be also factorized as 3x minus 1 times x plus 2. So f of x can be fully factorized as this one, that is 2x minus 1 times 3x minus 1 plus x plus 1, so that from each the roots of its linear factors, we can determine the root of the given polynomial function. Therefore, the roots are 1 over 2, which is the 0 of 2x minus 1, 1 over 3, which is the 0 of the second factor, 3x minus 1, and minus 1, which is the factor of the last linear factor, which is x minus 1. To sketch the graph, the degree is the usual one, that's simply 3 with positive leading coefficient. The roots are minus 1, 1 over 3, and 1 over 2, which are the expected x-intercept of the graph of the given function. The y-intercept is at the point at which f of x is 0, so that f of 0 is 1, therefore 0, 1 will be it is y-intercept. And when we put this information on the Cartesian coordinate system, the graph will look like this one. The y-intercept is this one, that's simply 0, 1. And the x-intercepts are 3, which are the zeros of the given polynomial function, which are minus 1, 1 over 3, and I think 1 over 10, yeah, 1 minus 1, 1 over 3, and 1 over 2. 1 over 3 and 1 over 2, so that they hit the graph. And we have seen previously, it is also the ends are increasing, so that when x gets a very large positive number, its functional value will also increase in the upward direction without any bound. The negative part, when x gets a very small negative number but with very large absolute value, so it goes down like this. So the graph is this one. Next, to execute minus 5x squared minus 28x plus 15. Possible roots are this one, which is the combination of the possible factors of 15 and possible factors of 2. So that if we check for x equal to 5, it is already 0, so that 5 is one of the possible rational root of this polynomial function. Therefore, if we apply a factor theorem, f of x can be, that is, if 5 is the root of this polynomial function, x minus 5 must be this factor. If we divide this one by x minus 5, so f of x can be written in this pattern, that is the quotient, which is obtained by dividing this cubic polynomial function by the first linear factor, that is x minus 5. But 2x squared plus 5x minus 3 can also be factorized as 2x minus 1 plus x, 2x minus 1 times x plus 3. Then totally the function f of x can be expressed or factorized as x minus 5 times 2x minus 1 times x plus 3. Then from the linear factors, the roots of the given polynomial function are 5, 1 over 2, and minus 3. If you want to check this one within the possible roots of there, everything will be here. That is 5 is here, 1 over 2 is here. I think the next one could be, that is negative 3, which is negative 3, which is around here. That's simply this one. Therefore, this is what rational root test is. And when we proceed to the graph of the given polynomial function, the degree is 3 again, which is positive leading coefficient again. The roots are this one, which are the expected x-intercepts. The y-intercept is obtained when x is equal to 0, which is f of 0 is equal to 15. Therefore 0, 15 will be this y-intercept. Then the graph roughly could look like this one. This is the y-intercept 0, 15. This is minus 3, which is the first 0. 1 over 2, 0. The second root end, the third rational root would be 5, 0, which is the x-intercept of the graph. So the ends of the graph are increasing, that is in the upward direction in the right side, and goes in the down in the negative direction, the left side. Question number 13. Just analyze and sketch the graph of these rational functions. So let us try to see one by one. We know that in order to graph the graph of every rational function, we have to know or simply know first the basic components or simply procedures. First, we have to determine its domain, and we have to fix holes if there are, and vertical asymptotes, or simply general asymptotes. The vertical asymptote here is x equals 3. We know that x equals 3 is said to be the vertical asymptote of this one whenever 3 is not within the domain of the given function, and if it is not removable, or simply if it is within there, so that the vertical line which passes through this point, that is x equals 3, is said to be the vertical asymptote of the graph of this rational function. And horizontal asymptote depends on the degree of the numerator and the denominator. We know that here the degree of the numerator is 0 and the degree of the denominator is 1, so that in this case the line that is y is equal to 0, or the x-axis, could be taken or considered as the horizontal asymptote for the graph of this rational function. But whenever the graph of the degree of the numerator is exactly equal with that of the degree of the denominator, the horizontal asymptote could be the quotient of, that is the vertical line which passes through the quotient of the leading coefficients of the numerator and the denominator. They hit the possibility where the given rational function has a horizontal asymptote. Therefore, the x-intercept could be, there is no x-intercept, because whenever f of x is equal to 0, we have a false statement that simply 0 is equal to 4. Therefore, the graph can never intersect the x-axis, because already the x-axis, that is the horizontal axis y is equal to 0, is considered or simply calculated to be the horizontal asymptote. The y-intercept could be whenever x is equal to 0. When x is equal to 0, we have negative 4 over 3. Therefore, 0, negative 4 over 3 would be the y-intercept. And if we combine this one, that is, it is a hyperbola. The vertical asymptote is this one. Horizontal asymptote is the x-axis, which is y is equal to 0. The y-intercept is 0, negative 4 over 3. Quadrants are the first quadrant and the second, the fourth quadrant. Therefore, the graph looks like this one. This is the vertical axis, the vertical line that is x equal to 0, which is the vertical asymptote, and the x-axis y is equal to 0 is the horizontal asymptote. Here, the property of the graph near the vertical axis is that when x approaches this one, that's simply 3, from the right side, the functional value of the given function will tend to the very large positive number, that is to the positive part. So that this will determine the property of the graph of the given function. Then when x goes to that of a very large positive number, the graph will approach the horizontal axis, that is the x-axis, but it may never intersect or simply touch the horizontal asymptote. Similarly to the left side of the vertical asymptote, when x approaches 3 to the left or simply from the left side, the functional value of the given function, or simply f of x, will tend to that of very small negative number, that's simply down. And when x goes to that of negative infinity, so that the functional value will approaches the given horizontal asymptote or the x-axis from below. So the graph of the given function will looks like this. And then a hyperbola, which is found in the first quadrant and for first and around fourth quadrant. Okay, the next one could be this one, that's question number 13b. F of x given by this rational function. So first, let's factorize first. F of x, the denominator could be factorized as, that is trying to finding the two real numbers whose sum is 7 and whose product is 12, that is 3 and 4, so that x squared plus 7, x plus 12 could be factorized as x plus 3 times x plus 4. And the denominator, that is, if we factor out 2 or minus 2 at the common factor first, it could be x squared minus plus x minus 6. And the factorized form of x squared plus x minus 6 would be x plus 3 times x minus 2. Then we have similar factors here, x plus 3, x plus 3, so that they can be cancelled. But in this case, the domain is should be restricted first, that is x must be different from that of minus 3 and positive 2. So at x equal to minus 3, because the common factors can be cancelled, therefore x equal to negative 3 cannot be a vertical asymptote, rather we will put a hole there, a hole at x equal to minus 3 at the simplified form. Then vertical asymptote is only this one, which is, it is irremovable, that is x equal to 2 is a vertical asymptote. And the horizontal asymptote could be, since the degree of the numerator and the denominator are equal, that is simply 2, so that the horizontal asymptote could be the line which passes through the quotient of the leading coefficient of these two, that is 1 in negative 2, which is negative 1 over 2. Therefore, the information for the graph of this rational function could be, we have the x-intercept, that is the numerator is equal to 0, x equal to minus 4, not minus 3, since we have a hole here. And the y-intercept is whenever x equal to 0, it becomes 12 over 12, but that is simply 1, so that 0, 1 will be its y-intercept. And the whole at x equal to 3, using the simplified form, the point that we put with the whole could be f simplified could be, that is when x minus, or I mean x plus 3 is removed or cancelled, we have this one, so that f of minus 3 at the simplified form will be minus 10. Therefore, at minus 3, 1 over 10, there is a hole for the graph of the given function. Then sketching the rational function with hole, vertical asymptote at 2, horizontal asymptote at this could looks like this. They hit the vertical asymptote. The horizontal asymptote is this one, the dotted line, the red dotted line with y is equal to negative 1 over 2. And they hit the x-intercept, which is minus 4, 0. The y-intercept is 0, 1. So that the property of the graph and near the vertical asymptote x equal to 2 will be, from the right, the graph approaches the vertical asymptote and it approaches the horizontal asymptote from below. Similarly, from the left side of the vertical asymptote, when x approaches the vertical asymptote x equal to 2, from the left side, its functional value will increase indefinitely. And when x gets a very small negative number, that means x tends to negative, so that it will enter, the graph will intersect the x-axis at minus 4, 0, and it approaches the horizontal asymptote, that is y is equal to negative 1 over 2 from above. And there is also a hole here, that is this hole, that's simply this one, which is obtained at negative 3 and negative 1 over 10, I think negative 1 over 10, so that this is the hole. Therefore, this is the rough sketch or simply graph of x squared plus 7x plus 12 over minus 2x squared minus 2x plus 12. The last one could be minus rational function minus 3x plus 12 over x squared minus 3x minus 2. Here, first, let's factorize again. F of x equal to minus 3 into x minus 4, and the factorized form of x squared minus 3x minus 4 could be x minus 4 times x plus 4. So we have x minus 4, we have x minus 4, they can be cancelled. Therefore, at x equal to minus 4, the graph will have a hole like that of the previous one. So the domain first, x must be different from that of 4 and minus 1. And there is a hole at x equal to 4 because it is removable. A common factor can be cancelled. A vertical asymptote is x equal to minus 1. That is the point at which the function is undefined. And the horizontal asymptote could be, since the degree of the denominator is less than that of the degree of the denominator, so that the horizontal axis, which is y is equal to 0, or the x-axis could be the horizontal asymptote for the graph of this rational function. Then the information for the graph of this function could be the x-intercept would be x equal to 4, but that is a whole. So the graph doesn't intersect the horizontal axis, because already the horizontal axis or the x-axis is a horizontal asymptote for the graph. The y-intercept is f of 0, which is equal to 12 over negative 4, which is negative 3. Therefore, the graph intersected the the vertical axis at 0, negative 3. There is a hole at 4. Then, in order to specifically put the point, we have to take the simplified form of the given function. So the simplified form is negative 3 over x plus 1. Therefore, the functional value at 4 for this one could be negative 3 over 5. Therefore, the whole of the graph will be 4 with negative 3 over 5. Then the rough sketch of this graph, this rational function with this information, with whole at negative 3 over 5, vertical asymptote at 1, and horizontal asymptote at 0, or simply x-axis could be this one. That means the vertical asymptote, x equal to minus 1. There is the horizontal asymptote, that is y is equal to 0, or the x-axis itself. And the property of the graph of this function near to the vertical asymptote could be from the left side when x approaches to minus 1, that is the vertical asymptote from the left side. It goes in the upper direction, and the graph approaches the horizontal axis, or simply the horizontal asymptote from above. That means when x gets a very small negative number, the graph approaches the x-axis. And from the right side of the vertical asymptote, when x approaches from the right side, x will approach, or simply tends to that of negative infinity. And when x approaches, or simply gets a very large positive number, its functional value will, or simply graph will approach the x-axis or the horizontal asymptote from below, so that roughly the graph of the given function looks like this. Okay, that is all what I have for today. I guess we'll meet by other questions like this the next time. Thank you for watching. Don't forget just to subscribe this channel for more.